working as assistant professor in the Department of Electrical and Electronics Engineering, SRM Institute of Science and Technology, Ramapuram, Chennai. I'm here to present my title, Driving Train-Based Optimization Technique for Estimation of Synchronous Motor Excitation Current. And my co-author is Dr. Rengaraj, Associate Professor, Department of Electrical and Electronics Engineering, SSC College of Engineering, Kalavakkam. And the objective of our paper is to introduce an innovative application of driving train-based optimization technique to optimize a multiple linear regression model for estimating synchronous motor excitation current. This is actually inspired by the driving training, where the driving teacher will teach his students how to drive a vehicle. Based on that, an optimization algorithm is being developed to accurately determine the regression coefficients, which is having a faster convergence. The DTBO-based MLR model is compared with other optimization techniques such as the Gravitational Search Algorithm, artificial bee colony, genetic algorithm, Symbiotic Organisms Search, and various machine learning algorithms. Using an experimental data set of 557 samples, out of which 390 were used for training and 167 used for testing, the DTBO-based model achieves a better optimization function value, which is a minimum value, demonstrating superior performance in minimizing estimation errors. Key metrics like maximum error, error percentage, standard deviation, and root mean square error validate the results. The DTBO-based approach not only outperforms the other methods, but also provides a clear mathematical relationship between an excitation current and input features. This enables a very easy way to hardware implementation. This study establishes the DTBO-based model, MLR model, as a robust and efficient alternative to complex machine learning algorithms for estimating synchronous motor excitation current, offering significant contribution to power system engineering and smart grid. And simple introduction about the usage of the synchronous motor. The synchronous motor is basically used in an overexcited mode to supply reactive power into the system, thereby improving the power factor of the system. Example here in this diagram, you can see that these two induction motors are connected to an infinite bus bar. The induction motors are having a low power factor, which is being compensated by the reactive power injected by the synchronous motor into the infinite bus bar. And Q1, Q2 are the reactive powers are taken from the bus bar, whereas Q3, Q4 are the reactive power injected into the bus bar for improving the power factor of the system. So the synchronous motor basically have the capability to operate in three different power factors, starting from lagging power factor, leading power factor, and unity power factor. Here, the overexcited synchronous motor is also called as a synchronous exciter, which is basically used for improving the power factor of the system, as well as maintaining the reactive power in the infinite bus bar. And maintaining the reactive power as well as the power factor plays a vital role. For that, different researchers have proposed different methods for estimating the parameters of the synchronous motor. Example, so artificial intelligence-based modeling technique, including proportional integral derivative control, pulse width modulation, Kalman filtering methods, and other artificial neural networks are being used in the literature review for exploring the options available. And apart from that, various optimization techniques have been suggested, including particle swarm optimization, k-nearest neighborhood estimator, enhanced by genetic algorithm, adaptive artificial neural network, artificial bee colony, gravitational search algorithm, and symbiotic organisms search algorithms are used in the literature for estimating the parameters of the synchronous motor. Apart from that, we have also introduced machine learning algorithms, implementation of the machine learning algorithms like supported permission, decision trees, and extreme gradient booster regression for this research work to forecast the excitation current of the synchronous motor. So there exists a significant research gap in developing a model that not only accurately predicts the excitation current of synchronous motor, but also offers a most transparent and computational efficient approach. To address this gap, a multiple linear regression model has been proposed, which conveniently represents the excitation current in terms of four input parameters, starting from the load current, power factor error, and change in excitation current. Previous studies have employed other optimization algorithms to estimate the regression coefficients of the MLR model. With the quality of this coefficient directly influence the model performance. However, the application of training-based optimization technique has not been explored, and this training-based optimization technique performance is already compared with other optimization algorithms, and it has been shown widely showing the superior property of the DTBO algorithm when compared to the other algorithms. And for our research work, the multiple linear regression model for estimating the excitation current, IL is the load current which is to be estimated by the given algorithm. We have used 4 input parameters starting from the load current, power factor error, and the change in excitation. The last component is the output, that is the target, which is to be estimated by the other 4 parameters. So equation 1 shows the estimated the excitation current of the synchronous motor, which is a function of 4 parameters: load current, power factor error, change in excitation current. It has linearly related with the help of the multiple linear regression, C1, C2, C3, C4, C5 are the regression coefficients which are used for estimating the excitation current. So here we use the power factor error, which is given by the reference power factor minus the system power factor. The reference is the actual target or the expected power factor to be maintained by the system, whereas cos-y system is the power factor that is available in the system. The change in excitation current is calculated by subtracting the previous sample of the excitation current with the current sample. So IL load current, it is measured in the system using the meters. Power factor, it is also measured with the help of the power factor meter. Power factor error and the change in excitation current are calculated based on the formula given in equation 213. And now we can form the entire system as a matrix, like IF1 is the field current first sample, excitation current first sample. IF2 is the field current second sample. Example IF1 is depending on 5 regression coefficients: C11, C12, C13, C14, C15, and the 5 factors are IL1, PF1, E1, del F1, which is the change in excitation current. 1 here represents the bias, and our objective function is minimize the excitation current estimation error, which is given by equation 5. The function is given by summation I equal to 1 to n, IF estimated minus IF actual the whole square. We are finding the sum of the square error. And after that, we are going into the DTBO algorithm, how the algorithm is implemented for estimating excitation current. So here first we are generating the population matrix of DTBO. It consists of the C matrix starting from C1 to Cn. It's a n cross 5 matrix. N represents the number of samples we have taken. 5 we have already discussed in the previous slide. That is the number of factors starting from IL1, PF1, E1, del F1, and then the last one bias. For all these 5 variables, we have introduced the regression coefficients. And Cij stands for it is calculated by using the formula LBJ plus R into EBJ minus LBJ, where LBJ is the lower bound value of the given variable, that is the regression coefficient, and EBJ is the upper bound of the variable, where the upper bound is we have taken as 1 and the lower bound we have taken as 0. And the objective function is derived from the initial regression coefficients. So first we will randomly generate the values of the C matrix. Based on the C matrix, we will calculate the parameters IF1, IF2, IF3, like that. For all the field currents, we will calculate the, we will estimate the field current using the formula. And after that, we will calculate the error. Once the error is calculated, we will try to minimize the error. And the 3 stages of the DTBO algorithms are given here. The first one is the exploration stage. So the exploration stage is given by forming the BEEI matrix, which is the driving instructor matrix. It consists of BEEI 1 to I5, representing the 5 factors. So this BEEI matrix is updated every iteration, and the number of training instructors are basically derived based on the given sample. Actually, we are having around a 560 sample, out of which 480 we have taken for training the system. In that 480, randomly some variables, some samples will be taken as the training instructor. Based on that, the weights will be updated. This is in the phase 1. So next one is the phase 2. So here the driving instructor will capture in the phase 1, the driving instructor will capture the pattern that is existing between the variables. Accordingly, the weights will be updated, and the the coefficient, regression coefficient values will be updated. And in the second phase, patterning of the instructor skills of the driver students. From the driving instructors, the observers will, or the student will observe the driving skill, that is the phase 2 of the DTBO algorithm. And the DTBO algorithm phase 2 is implemented with the help of the 3 equations, equation 13, equation 14, and equation 15. And once the students learns from the driving instructor, the third one is the training by the driving instructor itself. This phase focuses on individual enhancement, allowing the learner to achieve better performance through self-directed improvement. And this is basically achieved by equation 16 and 17. So altogether, all the 3 phases are explained with the help of the flowchart given in figure now shown in the screen. So initially, we are giving all the values we have, all the samples we have connected as n training samples. That is the first step. And then we will set the number of agents and the number of iterations. And randomly, we will select the regression coefficient, that is the C matrix. Once C matrix is selected, then we will calculate the excitation current based on the equation number 1. From there, the objective function will be calculated using equation 5. And after that, the 3 phases of the DTBO algorithms are repeated until the maximum iteration is reached. Once the maximum iteration is reached, the best possible solutions are captured, and the best possible solutions will give you the regression coefficients of the quasi-optimal solution of the objective function found by the DTBO algorithm. And after updating the regression coefficients from phases 1 to 3, 1 iteration will be over. And as per the number of iterations set in the system, the iterations will be repeated until the maximum iterations is reached. Once the maximum iterations is reached, we can get the optimal regression coefficients by effectively balancing the exploration and exploitation stage within the solutions stage. The advantage of the DTBO algorithm is we are giving the solution space where the algorithm searches for the best possible values in the in the solution space provided by the user. Here we have taken the regression coefficient ranges 0 to 1 because the negative coefficients are not possible, only positive coefficients. So we have selected the values as the lower bound as 0 and the upper bound as 1. In that 0 to 1 region, the values will be selected. And at the end of the maximum iteration, the best regression coefficients are identified, and it will give you a most effective solution for the objective function. And before going to the results and discussion, the samples of the training and tested data, a few 10 samples are provided in the table. So the first column represents whether the given sample is a training or a testing sample, and the second column represents the sample number, and the third column represents the field current, load current here. The fourth column power factor, and the fifth column the error E, and the sixth column delta. Again, the difference between the previous sample and the present sample, its unit is also here. And the last column is the excitation current here. And the various parameters required for tuning the parameters of the other algorithms are given here, along with the proposed implementation of the DTBO algorithm. Here, the number of agents we have taken as 30, and the maximum iteration we have chosen as 1000. And the pictorial graphical representation of the excitation currents of the training samples are given here, where the x-axis corresponds to the training samples and the y-axis corresponds to the excitation current. Similarly, the test samples are graphically shown here, with the x-axis as the index of the test sample, y-axis as the excitation current. And now after optimization, test score is plotted here, and here the advantage of this DTBO algorithm you can see in the graph. Once the iteration crosses the convergent, the function starts converging, and here while attaining when the iteration reaches 20 itself, we are able to get the best solution for the given system. And this table will give you the regression coefficients for different algorithms implemented by the system, starting from SOS, GSA, ABC, GASA, DTBO-based algorithm. Here C1, C2, C3, C4, C5 are the 5 regression coefficients, which we have optimized by using the different algorithms. And the last column gives you the objective function value. Here from this table, we are able to understand that the DTBO-based algorithm has a minimum objective value when compared to the other. And the advantage of the implementation of the DTBO-based algorithm, here you can see equation 18, which is having a showing a direct relation between the estimated field current with the parameter input features we have taken, starting from IL, FD, LIF, and the last one, the bias. And this simple equation can be easily implemented using an hardware algorithm, which is not possible when compared to the other machine learning algorithm, because it will act as a black box. The relation between the input and the output are not explicitly shown in the algorithm. And the performance can also be compared with the help of the actual value as well as the estimated field current using this figure number 4, where x-axis is your test sample index and y-axis is your excitation curve. Next one, we could see that the maximum error obtained by using the DTBO is much better than compared to the other algorithm. We have also tried with the machine learning algorithms like support vector machine and based algorithms. Out of the RP algorithms implemented for estimating the synchronous motor excitation current, the proposed VTO-based algorithm gives a better performance in terms of the maximum error percentage, standard deviation, and root mean square error. To conclude, we have introduced and evaluated a DTBO-based multiple linear regression model for estimating the synchronous motor excitation current, and the model is is having a good capability to determine the regression coefficient with high precision, and the model has demonstrated superior performance in comparison to several established optimization algorithms such as GSA, SOS, ABC, and GE, as well as other machine learning algorithms. The results indicate that the MLR model achieved the lowest objective function value compared to the other algorithms. And the advantage of the proposed method is we have a simple equation given in the paper as equation 18, which can be easily implemented as a hardware by having a simple arithmetic logic. Whereas this cannot be possible using a machine learning algorithm, which will act as a black boxes, and that does not provide a clear relationship between the excitation current and the input features. This transparency makes the proposed model easily hardware implementation and faster computation. And also we have tried with the recent optimization technique for hyperparameter tuning using the Bayesian optimization and Python cross validation, but the performance does not surpass the accuracy and efficiency of the DTBO-based MLR. And the future work can be expanded for other nonlinear regression models such as polynomial or neural networks to capture more complex relationship by having a large number of data samples, so that implementing the DTBO-based MLR model in real time, such as smart grid performs, will also have a good practical performance. So this is the conclusion and the future work for the paper. We also thank the opportunity given for us to explain our paper, and these are the references we have used for the research work. Any further clarification regarding the execution of the model or implementation of the algorithm? with the relevant data set, the authors can be contacted with the mail ID that is given in the paper. We will also invite the other researchers for a collaborative work with our university. Thank you. Thank you so much.